Okay, so last class we started on the coupled cluster theory. We motivated a little bit towards why an exponential ansatz, which is a guess for the form of the wave function, is probably a good guess, which at least satisfies the requirement of size consistency in a non-interacting system. Now, we also started working on how to get the equations to determine the variables in this theory, which are called cluster amplitudes. So let's just recap a little bit and then we'll go ahead with getting the working equations. So we have the Schrodinger equation, and our ansatz is that the exact correlated wave function is a nonlinear combination of excited determinants and the Hartree-Fock function. And the nonlinearity is in the form of an exponential. So T is an operator which creates excited determinants out of the Hartree-Fock determinant, just like in a CI. But instead of just a linear combination of various excitations, we have an exponential combination. Now we substitute this in the Schrodinger equation. And then this is the starting point for my coupled cluster theory. So what we do is we multiply with e to the power minus t, which basically shifts all the operators to the left hand side of the equation, and we have the energy on the right hand side. Then to get the energy equation, as it is called, we project with the Hartree-Fock function, which tells me that the energy is basically an expectation value of this combination of operators for the Hartree-Fock function. And then to get the so-called amplitude equations, so what are the cluster amplitudes? Let me just mention that. So T is a sum over various excitation operators. So I can say I, J up to something, A, B up to something, of some cluster amplitudes and a corresponding operator. So this is what is called the excitation operator, and I can write it as so the E operator tells me that I'm exciting the or replacing ij spin orbitals in my Hartree-Fock determinant with virtual orbitals, which are obtained as byproducts from the Hartree-Fock calculation. And these are the coefficients of each operator, of each excitation operator, and these are what are called the cluster amplitudes. And these are analogous to the coefficients of the CI expansion of the wave function. So these are my variables now. Is someone saying something? No? Okay. And to obtain these cluster amplitudes, we need the amplitude equation. And the way that it is done is that you project with excited determinants. So every chi is basically some Eij, one particular operator acting on phi. And I can maybe call this a particular one, just to be clear. And depending upon what sort of truncated scheme you are doing, so the exponential is an infinite series. So you have here, so you have to choose the rank of excited determinants that you want to include. So the most common one being singly and doubly excited determinants. And that will tell you which excited determinants you need to project with. And this is done in a step-by-step fashion. So projecting with the singly excited determinants. So if you project with chi I to A, that will give you the equation for T I to A, the set. Okay. The equations for the singly excited cluster operators, or single excitation cluster operators, and you can project with the set of doubly excited determinants, and you get equations for Tij to AB, which are the doubly excited. And if you want triples, you go on and on and on. But they are not independent equations, so they are all coupled. So an equation for a particular excitation I to A requires or contains the variables, all the variables J to B, K to C, etc., as well as the doubly excited ones, IJ to AB, KL to CD, IL to DE, whatever. So all of them contain, so every equation contains all the variables, more or less. Okay. So which means that you have a huge set of non-linear coupled equations. That is the structure of your equation. So this is very different from the CI equation. So in CI, the equation that you needed to solve had the form of a diagonalization, or it was a matrix eigenvalue equation. And you adopted a Davidson procedure to get a few roots. Or if it's a small enough matrix, you can do a full diagonalization. So that was the mathematical method. In Hartree-Fock, you had an iterative diagonalization procedure. But in this case, you have a nonlinear coupled equation. So the method of solution is different. It is also iterative, and it is also, but it also is more expensive. Okay. So at this point, I'm only talking about the structure. We will have to, of course, get an explicit expression for the cluster operators. But to do that, we have to go through some more mathematical tools, which we will do a little bit later. But before that, let me try to tell you what other methods could have been possible to solve this equation. So, the standard method is to simply project with the excited determinants and get a set of nonlinear coupled equations. Now, what else could I have done? What else could I have done? I could have taken the coupled cluster energy expression and done a variational minimization. So this was the procedure for CI, or even for Hartree-Fock. So that is an alternative. But why is that not a good alternative in this case? Let's see. So let's look at alternative solution strategies for an e to the power t answers. So one is variational. So the energy expression is, or would have been, I've been writing 5. So this is psi dagger, expectation value of h. And because e to the power t phi is not normalized, it follows intermediate normalization, but not full normalization. So I have to divide by psi, the overlap. That is e to the power t dagger, e to the power t phi. So I hope you understood this expression. So this is basically psi h psi, and this is basically psi. And this is the expression that you would normally minimize variationally to get your equations for the variables. But see what happens. Let's say I only have single excitation, so the simplest cluster operator that I can think of. Even then, my pi e to the power t dagger h e to the power t phi, this one plus t dagger plus half t dagger square plus whatever. Then you have h in the middle, and then you have 1 plus t plus half t squared plus whatever phi. So this, in this, let's look at one particular term, the simplest non-trivial term, which is t dagger ht. So from this I am looking at t dagger ht phi, and t phi will create some excited determinant chi, and t dagger phi on the bra will create a chi, bra chi of the same excited determinant. You have an h in the middle. And this is basically an expectation value expression. And if you remember Slater's rules, these terms have the most complicated expression. And you will have several expectation values from every t operator in your set, in this case. So any t will give you an expectation value of h between two excited determinants. And you'll end up with a range of complicated expressions. Okay? And then, and also this would mean that there is no natural truncation of your t series as well. So if you take a t1, this expression is valid. If you take a t2, which is basically a double excitation, this expression will give you a contribution. If you take a 8 order excited operator, so T8, which means you're replacing 8 spin orbitals, 8 occupied spin orbitals with 8 virtual spin orbitals. Even those excited determinants will contribute even in the first linear term. So this is not a good thing, because this does not tell you where you can stop, either in the truncation of T1, T2, T3, or in the truncation of this exponential series. So it doesn't allow you to stop at any power of t or t dagger. Okay. So this is a very, very complicated expression with no natural truncation. Okay, and it also does not tell you any or indicates any sort of physical argument for truncation. because there is no reason for chi h chi for highly excited determinants to be smaller than chi h chi for a low excited, so singly or doubly excited chi. So there is no argument there. So basically you end up with with an infinite number of terms and no logic to reduce the numbers. So the only way you could proceed here was to arbitrarily truncate at some point without an argument, just because you cannot evaluate an infinite series. And that is never a good idea. So while this has been attempted or was attempted in the early stages of coupled cluster, this has not been really taken up in the future. And the desire that the coupled cluster energy also be a variationally optimized energy, which would mean that if this is an upper bound to the exact energy, this requirement was abandoned because the working equations were too formidable. Okay. So we abandoned this, which means that the coupled cluster energy is not an upper bound. Okay. The usual coupled cluster energy here. So I'll write this down to record, just for record. So this energy here, this is not an upper bound to E exact because it is not variational. So if you have an inaccurate coupled cluster calculation, your energy may be below the corresponding full CI energy, which you can calculate. You cannot calculate the exact energy, so I cannot give you a numerical comparison for that. But the full CI is a variational theory, and if you have the full CI number in the same basis set as the coupled cluster number, your coupled cluster number it is allowed that it goes below the full CI. It is not a common occurrence. It is normally above, but it can happen. Also, the numerator is complicated in the variational approach. The denominator is also actually infinite. So you don't have a finite norm in this case either. Okay. So this is more or less an abandoned approach. Then the next thing, okay, a related thing which is important to note is that the coupled cluster energy expression my tablet does not scroll well. Okay. In the coupled cluster energy expression, you have e to the power minus t, h e to the power t. And this operator is not a Hermitian operator. Okay? So, what this is called is that this is a similarity transform of H, but it is not Hermitian. So this is again another thing that is not desirable in a way, because the in quantum mechanics, it is one of the fundamental postulates that observables are expectation values of Hermitian operators. But the coupled cluster energy is now an expectation value of a non-Hermitian operator. So this is not something desirable. But what makes it acceptable is that this operator has an energy spectrum which is identical to the Hermitian operator H. So if you have a full expansion for T, it can be shown that a similarity transformed Hamiltonian has the same energy spectrum as the bare Hamiltonian. So let me put that down as well. Where can I put it? Use a different color. So without truncating T, e to the power minus th e to the power t has same energy spectrum as H. So this is what makes it acceptable, even though it is not a Hermitian operator. Now, from this sort of hiccup in the theory, to avoid this, a second alternative approach was envisioned, which is unitary coupled cluster. So what is unitary coupled cluster theory? Unitary coupled cluster theory, sometimes called UCC, is where instead of e to the power t, as in the original, you take e to the power t minus t dagger. So what good does this do? If you take the ansatz to be e to the power t minus t dagger, then t minus t dagger is a anti-Hermitian operator, and an exponential of an anti-Hermitian operator is a unitary operator. So e to the power t minus t dagger becomes a unitary operator. So if it is unitary, then my energy expression becomes phi e to the power t dagger minus t h e to the power t minus t dagger phi, and this is now Hermitian. Okay. So this is but then you see again we have both t dagger and t on the left and right, and because of the same argument as variational coupled cluster, you end up with infinite series of terms in your working equation, which again becomes unfeasible. Okay. But you also get infinite non-truncating series of terms in your working equation. Okay. But for unitary coupled clusters, some attempts have been made to provide perturbative arguments for choosing terms from this series, allowing some sort of truncation based on perturbative arguments. Now, why I mention unitary coupled cluster now is because with the advent of quantum computers, the most suitable theory for application in quantum computers has now become unitary coupled cluster. So, the reason is that among the operations that are possible on a quantum computer, you can, the application of unitary operators on a wave function is possible on a quantum computer. So you cannot do all classical operations on it. You can only do some specific operations, one of which is the application of a unitary operator on a wave function, and the unitary coupled cluster sort of directly does exactly that. So that is what you need. You need to apply a unitary operator on a wave function. So it has started receiving a lot of attention. So it had become a very quiet theory because it's so difficult to calculate. And the advantages are not that much over and above the simplest approach of projecting with the excited determinants that I spoke of first. So it had become sort of a dormant theory, but with quantum computers, people have started looking at this again, because this has a lot of desirable theoretical properties. Okay, so the unitary coupled cluster can be related to a variational theorem. It can be, like I said, the energy is then an expectation value of a Hermitian operator. So these things are desirable. The problem was you had to evaluate lots and lots of terms, which made it computationally very expensive and also very difficult algebraically to get correct expressions. But if you have a quantum computer, you don't need to open out the series, so to speak. So you can use the unitary operator as a whole, at least as far as I understand. I'm not an expert on quantum computers, which is why there is renewed interest in the unitary coupled cluster. Now, other than this, there is also the prospect. So I'll talk about a third option. The third option is sort of a CI form of CC. So this is more or less simply instructive. It's not something that is practically done or was ever practically thought possible to do. So I'll just show you an analogy of what it would look like. So HCISD. So if you see the matrix that you need to diagonalize for a configuration interaction singles doubles, it has this form. These of diagonals are 0 by Brillou's theorem, and then you have the cross terms with the doubly excited. So let me put the diagonals down first. And these are the matrix elements that you need to evaluate, and then you diagonalize this matrix. If I wanted to do the same thing for CCSD, it would look something like this. But now I don't have a Brillou's theorem. Why? Because when a matrix element of the similarity transformed Hamiltonian of e to the power minus t h e to the power t between the ground state and the singly excited state contains not only the linear term but also the squared terms. So this is not 0. Okay. Then you also have the doubles, singles. These are different values, of course, from CI. So although I'm just writing using the same notation, they are different values. Okay, what I can do is I can put some bars here. So h bar CCSD is e to the power t h e to the power t. So then you will not get confused. So it's like this. And what about this side? So here, so 0s is basically when I am projecting the so 1 second. Yeah, so here you have the excitation operator. So T is always an excitation operator. So when you have h e to the power t, you only get the matrix elements where the ket has the excited function. You don't get the other the bra. If you okay, no, let me do it this way. So in order to obtain the cluster amplitudes, the equations that I have solved are basically things that look like chi I to a h bar phi equal to 0 and chi I j a b h bar phi equal to 0. So these are the equations for determining the couple cluster amplitudes. So these are the equations that I have solved, and these are exactly the matrix elements which would go in here. So these are 0. Okay. But once I have obtained the cluster amplitudes Ti to A, Tij to AB, etc., I can construct now phi h bar chi I to A, etc. And this is what goes into my couple cluster matrix. Okay. So if I construct the matrix which on diagonalization would give me the couple cluster energy, it would look like this, which is somewhat similar but also different from the CI matrix. Okay, so this also tells you that the matrix you're diagonalizing for CI is a symmetric matrix and is also a okay, so this is symmetric and the couple cluster matrix is not symmetric. Which means that also that if you diagonalize h bar to get right hand eigenvectors, so I guess you are aware that you can diagonalize a matrix to get right eigenvectors as well as left eigenvectors. And if it is a symmetric matrix, then the left and right eigenvectors are the same. However, if a matrix is not symmetric, then the left and right eigenvectors are different. And from this you can see that in couple cluster, left.
Ma'am,
Yeah.
in the matrix of the HCISD,
Yeah.
so the first means 1 cross 1 element, what you have written in the suffix of energy.
Over here, this is SCF.
Okay.
Yeah. So this is
And
the Hartree-Fock energy.
yes, that. And another question that uh, in the couple cluster matrix, why the second means chi ijb Hamiltonian phi is 0.
Oh, why this is 0? So these are basically the equations that you need to solve to get the values of the cluster amplitudes. They are the coefficients of your wave function expansion. So here I am constructing H bar CCSD after I have found the values of the T. So this is not something. So coupled cluster equation cannot be solved by a direct diagonalization, but once you have obtained the clustered amplitudes, you can construct the matrix which on diagonalization would have given you the coupled cluster energy. So this is a back way of doing it. Just to show you the structure of the two equations. So you still solve these two equations in the nonlinear coupled equation form. And because the equations have this form, that so this is basically H bar S0 and this is H bar D0. So those are the ones you have set to 0 to get your equations, and your cluster amplitude satisfy these two equations. So these two matrix elements over here will be 0. And the remaining quantities you have not used to determine your cluster amplitude. So after you have determined amplitude, you can compute them. And they are not necessarily 0. They can be some value. Okay. So after you have obtained the set of cluster amplitudes, you can construct H bar 0S, H bar 0D, etc., etc. You can construct all these things and put them in this matrix. And if you now diagonalize this matrix again, you will get back your coupled cluster energy. So why I wanted to show the structure was to compare with the CI matrix. So basically, there are two important points here from this. Okay, so one is the one I was writing. Let's write that first. In coupled cluster, left and right eigenvectors are different. Then, and the other thing that I wanted to point out was there is no Brillouin theorem for H bar. So what we are trying to do is we are comparing the matrix of H and H bar. So I told you that H and H bar have the same energy spectrum. Have exactly the same if T and e to the power T are not truncated. If I compare, on the other hand, a CISD and a CCSD, then H and H bar have fundamentally different matrices. And why are they different? Because they are so symmetric versus non-symmetric. Different entries are 0. Okay. And there is no. Okay, I wrote that. Okay, I repeated. No Brillouin theorem for H bar. Fine. And at this point, I can also mention that you can have additional. So you need additional theoretical machinery to compute the left eigenvectors of each part. But you don't have to. This is not important for you. This is more advanced than necessary. But I just wanted to mention that because this is a non-Hermitian expression e to the power minus th e to the power t, there are additional complications involved, and you lose certain amount of theoretical rigor in a way. But the results are very, very good, and it does, and it is the most feasible and most accurate theory till date. So we will go with it. So let me just go back to what is actually done. So now I spoke about three sort of alternative ways of looking at couple cluster. This may be a bit difficult to digest when you don't know what the usual couple cluster is. But hopefully when you come back after you have a better understanding of the ordinary couple cluster, you will be able to see why these strategies were not adopted. Sorry. Okay. So let's get back here. So what is the missing piece? So we know the form of the cluster amplitude equations that we need to solve. So I'll put them down here again. So these are the equations that I need to solve. So I guess you can see where we are stuck now. So what the next step should be is how to evaluate this. Okay. So last class I mentioned the Baker-Campbell-Hausdorff expansion, which tells you how to write this similarity transformed expression in terms of exponentials as a series of nested commutators. Okay. But now we have to make use of these nested commutators to evaluate the matrix element. So eventually what do we need? Eventually we need an expression which has the Hamiltonian integrals and the variables which are the clustered amplitudes. So those are the only things we know. We know the integrals of the Hamiltonian in the molecular orbitals, molecular orbital basis that we had generated from our Hartree-Fock calculation. So we had generated molecular orbitals from our Hartree-Fock calculation, and we can calculate the matrix elements of the Hamiltonian, either the 1 electron integrals or the 2 electron integrals. So those are the known quantities. We don't know anything else. So our ultimate expression should have only those. But how to get there? Okay. So let's go back to that. Working equations. So the first important thing here is the Baker-Campbell-Hausdorff expansion, sometimes called BCH or sometimes called only Hausdorff. And what is the expansion? The expansion is And we have also written our Hamiltonian in terms of second quantized operators. You can see that that is what will be required here. And my T operators, what do they look like? So T1 looks like this. T2 looks like this. Fine. So what will we have when we put back H and T in my Hausdorff expansion? I will get these strings of creation annihilation operators. And these creation annihilation operators, you have in the Hamiltonian, they have general orbital labels. So P and Q can either be IJKL or they can be ABCD. But in the T's, you have specific labels. So you have A and I, so they're distinct. The creations always have ABCD labels and the annihilations always have IJKL labels. Because they are constructed so as to construct excited determinants from the Hartree-Fock determinant. And when you apply the anti-commutation rules of creation and annihilation, so if I am going to evaluate, for example, the action of this on phi, like we have done before, we would want to move the AI dagger-like things to the right to annihilate phi, or AA, so annihilation of electrons in virtual orbitals or creation of electrons in occupied orbitals. So those operators I would want to move to the right so that the Hartree-Fock determinant gets annihilated and I reduce terms. Do you remember from I think 2 classes ago that we showed that if you evaluate commutators of operators, then you reduce the length of the string of creation annihilation operators. Let me go back to that and try to show you the, okay, that was quick. Okay, so we have evaluated a commutator of an operator with a general index and a specific index. So what is this basically? So this is basically the one body part of H, operator accompanying the one body part of H, and this is basically a T1 operator, right? And we saw that when we evaluated this, we ended up with 2 terms with only a pair of creation annihilation operators each. So we had started out with a string of 4 operators, or 2 strings of 4 operators, and we end up with 2 strings of 2 operators and a delta function. So the ranks of the operators get reduced every time you evaluate a commutator. So if you think about that, then you can sort of feel that the Hausdorff expansion with nested commutators will help in reducing the length of the string step by step. So if you have an HT commutator, you reduce the, so if it's HT1 or H, one body part of H and one body part of T, then from the expression that I showed just now, you will reduce the four length, string of length 4 to string of length 2. Also, when you have the two body part of H and the one body part of T, you will reduce a string of length 6 to a string of length 4. So that will keep getting reduced in the first commutator. Then if you have two commutators, then with the reduced strings, you will again take another commutator. So that will reduce it further. So, and at some point, you will exhaust the general indices of the Hamiltonian. So you have at most 4 general indices in the Hamiltonian. Okay. So the highest rank of nested commutators that you can have is basically 4. So the next term, HT, 4 T's. Because every time you evaluate a commutator, you will lose one general index. So at one point, you will lose all 4 from the Hamiltonian, and you cannot have a fifth commutator then. So the fifth, so beyond the fourth commutator, your Hausdorff expansion will terminate. Does this make sense to you? I'm trying to. So it's not something I can work out, because then it will take pages and pages. So I hope you're getting the drift. So the thing is that every time I do a commutator, I reduce a pair of indices. Okay, and you can think about it in this way, that since the T's have specific indices and the H has a general index, the T's will eat up the general indices of the Hamiltonian. So when you have 4 T's, then each T will eat up at least one general index of the Hamiltonian. So the highest rank of nested commutator that I can have in the Hausdorff expansion is 4. Okay. So this expression will naturally truncate at the fourth nested commutator due to the BCH expansion. So which term is that? HT, T, T, T. So that is the last one that you can have. And that is basically the one where the H is two body and these are T1s. So it's not as formidable as it looked. So what looked like an infinite series of terms to be evaluated is not actually so. It just stops at the fourth commutator, which is quite reasonable. Okay. I hope that is somewhat clear. But now, okay, the other thing which is obvious if you work it out, but I will still mention it because you are hearing it. That is the T operators commute with each other, but not with the Hamiltonian. Okay. Can you see that? So what does a T operator look like? AI, let's say J. So you have a creation annihilation and a creation annihilation on different orbitals. So what is the, what does, so let me call this T. Oh, what can I call it? T alpha, T beta, and then T alpha, T beta commutator. That looks like AJ minus AB dagger AJ I. And are the strings the same? Let's see. So let's try, let's keep the first one intact. So I want to move A dagger here. So this is delta AJ minus A dagger AJ. Now A and J are mutually exclusive, so that is not, that the term is not there. You only have minus A dagger AJ, which means a sign change. AB dagger AJ. Then when I change two creation or two annihilation operators, I only have a sign change. So two changes means no change. This will be and then I will again do that. This will give me a delta BI, which is 0, minus AI AB dagger. A minus sign. That is 0. Okay. You can try it for any one. So the T's always commute with each other because they have these distinct sets of orbitals in the creation and annihilation. But if, on the other hand, you have the Hamiltonian with general indices, then though the delta terms that I said were always 0 for the T's, those would remain because they are general T's or general indices. So the Hamiltonian does not commute. And we have seen that as well. We evaluated the commutator for H1 and T1. So what is the implication? So it means that the order in which you so if I am evaluating H, T, alpha, beta, gamma, that is the same as evaluating H, T, beta, alpha, T, gamma, or whatever other combination. So this is the implication of T's commuting. And because H does not commute again, HT minus TH is not 0. This is the implication of H and T not commuting. So you cannot move H around. You can move the T's around among themselves. So these are some points about the BCH expansion. And then now to get down to the integrals. So using this, if you actually used the BCH expansion and evaluated all the commutators using the anti-commutation relations, you would end up with a working equation. Okay, so it is possible to do it from this point, but it is very tedious. There is an additional mathematical concept or tool which is called the Wicks theorem, and that simplifies the derivation of the working equations. So that is the next thing we will do today. For now, you can just think of the Wicks theorem as an independent piece of knowledge, and then I will show you how to use it in the coupled cluster theory. So let's do Wicks theorem. Because I'm going to change my language a little bit and stop talking about the exponential answers for some time. Okay, so some more nomenclature. Okay. So there is something called a normal order or normal ordering of creation and okay, let me put this in the next page because this is really different. Oh, what happened? Normal ordering of creation and annihilation operators. So normal, okay, let me warn you also over here. So Wicks theorem is something that people ask a lot of questions on. Okay? So you can expect quite a few questions in your NSEM as well as in interviews. If you say that you know coupled clustered theory, you can be sure that interviewers will ask you questions about the Wicks theorem. Okay? So that is a very common thing. So it requires a little bit of thought and attention as well. So give it some attention when you study. Okay. No one will ask you to derive the coupled cluster working equations, but Bix theorem is a very popular topic. So normal ordering of creation and annihilation operators. What does it mean? It just means that you place all annihilation operators to the right of creation operators. So because there are so many varieties in how you arrange creation and annihilation operators, it was thought that if you specify a conventional order, it would become easier to handle these strings. So that if I tell you that I have a normal ordered string of 4 operators and I tell you the operators, you can immediately write them in the correct order. So the thing is that you place all annihilation operators to the right of creation operators. So if I want to write AA dagger and AI and AJ and dagger, if I want to write these 4 operators in normal order, I can write them either as AA dagger, AB dagger, AI, AJ, or AB dagger, AA dagger, AI, AJ. So so all of them are normal orders, or AA dagger, AB dagger, AJ, AI. So all of them are normal order. So it's not a very specific order. It just tells you that you must place all annihilation operators to the right of creation operators. And what is the advantage there? The advantage is that if you now act any normal ordered string on the vacuum, it will annihilate the vacuum. Which means that vacuum expectation values of all normal ordered strings are 0. So let me take an example, and I will copy it from the notes by Prof, because we will keep using this example for quite some time. Let me find it. Okay, yeah, got it. So I'm doing an example. So if I have an operator string, which is AP, AQ, dagger, AR, AS, dagger, then if I want to write it in normal order, I will, let's say, shift these two first. So this is delta PQ, AR, AS dagger, minus AQ dagger, AP, AR, AS dagger. Then I have delta PQ, and I shift this again. So that's delta RS minus delta PQ, AS dagger, R. Okay, and this is also there. So notice that AS dagger AR is already in normal order, so I have stopped tampering with it. Here I still need to get AS dagger this side. So this is then delta RS, AQ dagger AP plus AQ dagger AP, AS dagger AR. And delta PQ delta RS minus delta PQ AS dagger AR. So this is already now in normal order, AQ dagger AP. The last one still remains. One more step. So delta PS, AQ dagger AR minus AQ dagger AS dagger AP AR. Okay. So now we got our expression where all the terms are in normal order. So an operator which was an arbitrary string in an arbitrary order, this can be rearranged to give you a linear combination of strings which are all in normal order. So this is a little bit different from what I said here. So here I just told you that I have 4 operators write them in normal order. Then you can put them in any order, just maintaining the fact that creations come before annihilations. If I give you a particular string in a particular order, then, and I tell you write it in normal order, it will typically be a combination of strings in normal order, each of which is in normal order. Okay. Now let's verify the vacuum expectation value of A. This is a true vacuum expectation value. This is an empty state with nothing in it. So from the first term, we will get something. And from all other terms, we will get nothing. Why? Because the first operator over here, they will try to destroy an electron in an orbital, and there are no electrons in no orbitals in the vacuum. So all these terms will give you a zero contribution, and you get a very easy expression for your vacuum expectation value. So that is the one which has no operators whatsoever. Now I will introduce another term, and that is called a contraction. So we've already done a contraction. I've just not named it. So every time you get a delta function from a creation and an annihilation operator, when you want to interchange them, you generate an extra delta term. So every such delta term corresponds to a contraction. Okay, and when you have a contraction, it's called a contraction because it reduces the length of the string. Okay. So here the first term is what is called a completely contracted or totally contracted term, because you have lost all the operators. Here you have a single contraction, and this is just the normal ordered string without the contraction. But there is of course a formal definition. A contraction, it is said to be the difference in the original string and the normal ordered string. So I should also introduce the notation. So a normal ordered string is denoted by a bracket. So this is the operator for normal ordering. So what does that mean? So over here, okay, if I told you that A is this string, evaluate normal order A, then you would have done the same thing. Okay. So the brackets is sort of an operation which orders the string inside it. That is the best way of thinking about it. So here you see I'm still writing it as AB. I've not mentioned the internal structure of AB. So I don't know where the creations are, where the annihilations are. But I have put the operator with the curly braces over here, which means that whatever is inside, okay, if I have to remove the brackets, I have to put them in normal order. So it's like a mathematical operation, the brackets. And the contraction is defined. So it is written like this, where you put sort of a connection line between the operators which are contracted. So a contraction between two pairs of operators between two operators A and B is defined as the difference between the string original and normal ordered string. Okay. Also, since here the normal ordering is with respect to a vacuum, you can put a 0 here, or as they do in Prof in the notes, you can put a V here, which tells you that this is the true vacuum. You will see, we will change the vacuum a little bit later, so then you will see what happens. So this is what is called a contraction. And how would you use this notation over here? So over here, in this example, if you wanted to show the contraction, so I have just put a little arrow like this, right? But I could have said that this is, you know, with this sort of a arrow, that I'm contracting them here. But I'll show you exactly the perfect way of using this symbol. So I will not contaminate what we've done before. So the formal definition is this. Okay? But let's see. If A is now, if A and annihilation operators, let's see what happens. So if I have APAQ and I contract, okay, I have the original string and I have the normal ordered string. However, if you have two annihilation operators, whatever order they are in, they are. So you have APAQ minus APAQ, and that will give you a 0. And then you have, if you have two creation operators on the other hand, it's the same logic. This is equal to 0. Okay, fine. That is simple enough. Now, if you have something that looks like AP dagger AQ, sorry, contraction, this is also already in normal order, creation before annihilation, so this is also 0. If you have, on the other hand, AP AQ dagger, then you have AP AQ dagger minus AP AQ dagger normal order, and this is AP AQ dagger minus now delta PQ plus AQ dagger AP. Sorry. So this is the normal ordered string already. Okay. So this is just AQ dagger AP. So be careful. So you see, even after so much practice, I still made a mistake for a moment. So here you don't have to evaluate anything, because when you've put the bracket, it means the quantity that enters your expression is the result of the operation. It's the result of the normal ordering operation. So you would just reorder them and write it down here. And that is then APAQ dagger. This is just the minus of this. No. Wait.
Commutator bracket.
This is no. This is not the commutator bracket. This is the normal ordering bracket. So it tells you that you have to normal order what is inside. 1 minute. So I always get confused over here sometimes. So let's see. So AP AQ dagger minus AQ dagger AP. This comes with the plus. Yeah, this comes with the plus. So I evaluate this, and then this comes with the delta PQ. Yes or no? This is the normal ordered form of this. This is delta PQ minus delta PQ, right? AQ dagger AP plus. Why am I getting a negative sign? I should have just got a positive sign. So this is
Ma'am, the previously what you did was wrong or right?
previously what I did.
Minus AQ dagger AP.
No, that was wrong because so I need to put it in normal order. Okay, so okay, let just give me a moment. I will sort this out.
Maybe we can use commutation relation to convert AP AQ dagger to AQ dagger AP.
Yeah, so that is what I did now. But then also I am what I should get is just delta PQ. Okay. So there is so when you basically remove the normal ordering bracket, you just need to change the sign. So what it should be, well, what I can write from memory is this. Okay, so this is correct, and this is equal to delta PQ from the anti-commutation relations. But at the moment, I'm trying to think of how the logic came. So when you want to remove the brackets and you want to change the order of the string inside it, you have to just count how many interchanges are required, and you have a negative sign for each interchange. Okay, and that minus gives you a plus. So what I cannot remember exactly now is how to justify that rule. Uh, I've forgotten how to justify that rule. Just 1 minute.
Hello, ma'am.
Yeah.
In the normal order case, if I shift the position, then the sign already changed, negative sign. Maybe.
Yes, exactly. Yes,
But
that is the rule. That is the rule of how you do it. But I am trying to remember why that rule arose in the first place. So what tells me that that is how it should be? So it's true that if you have a string of normal ordered operators and you interchange any two operators to bring the string into the order where the creations come before annihilations, you count the number of interchanges and it's minus 1 to the power of that number of interchange. Okay. But how does that come about? So uh, so if I was to just do APAQ dagger normal order, what would I have done? I can say normal order delta PQ minus AQ dagger AP. I have delta PQ. I have minus of normal order AQ dagger P, and this is already in normal order, so I have delta PQ minus AQ dagger AP. Yes. But if I add now AP AQ dagger, and if I go back, then I will again have delta PQ plus AP AQ dagger. That is AP AQ dagger. That is not right, is it? That cannot be right. So this is the string that is already in normal order, which means the creation is in front of the annihilation. But the sign is not taken care of somehow. So that I can put down the rules. So the rule is that all operators inside a normal order V commute but gain a minus 1 to the power n sign for every interchange to bring it into normal order. But where does this rule come from?
Madam.
Yeah.
So what is the position for? I mean, what is the importance of true vacuum here?
So, the importance of true vacuum is that so that will actually come a little bit later. So, if depending on the vacuum that you choose, the actual order of operators, which is called normal ordering, that is different. So, instead of true vacuum, if you had, for example, a Hartree-Fock determinant as a vacuum, then if your orbital was labeled by a occupied orbital, you would want to put the creation operator to the right of the annihilation. So things which annihilate the vacuum go to the right. So that is more or less the universal rule. If it is the true vacuum, then that means that all the daggerless operators go to the right and the ones with daggers go to the left. If it is the Hartree-Fock vacuum, then in addition to looking at the daggers, you have to also look at the label. So we will come to that.
So
But
actually,
at this point, it doesn't matter. So at this point, we are not, we haven't got there yet.
so when you are doing the contraction in the second bracketed term along with the true vacuum, so I mean, what is the function? What does it do? Does it normal order, or I mean, what is the procedure for that term?
The contraction is basically represents a sum uh, over that index in a way. So, like I showed you over here, so when I wrote AP AQ dagger as delta PQ minus the reverse order, then the term delta PQ can be called a contraction of AP and AQ. Okay. So the if I want to define a contraction in terms of text, then a contraction is the expectation value of that string in the vacuum.
Ma'am,
So yeah,
here you have written that AP AQ dagger plus AQ dagger AP is delta PQ plus, but it should be minus, right? I mean, AP AQ dagger minus AQ dagger AP is delta PQ because
no, this is the anti-commutation of AP and AQ dagger.
yes, but AP and AQ dagger commutes, not anti-commutes. No, right.
No, they
Uh,
anti-commute.
okay.
Yeah. This is what it should be. What I'm a little bit confused about is, well, not confused. According to the rule, this is fine. That I have done one interchange and I have changed the sign. But I
Hello, ma'am.
can't remember how to justify the rule.
Hello, ma'am.
Yeah. Tell me.
I mean, in normal order, first operate the annihilation operator, then creation operator. In normal order, yes.
Yes. So
So
this is
that's
the normal ordered form. So here I have not yet normal ordered because I've kept the bracket, which means that that operation remains to be done. It has not been normal ordered. But I think what it means, okay, so I think that there's a little bit of a ambiguity in the notation here. So it basically means that I am normal, uh, that the contraction terms are not included in the operation of the brackets. So when I do this and I write it in normal order, if I write A in normal order, then I get some contracted terms and I get the string in normal order. But when I just say evaluate this, okay, then I do not evaluate the contraction terms. Okay, so this just means that I write the string in normal order, and this is the sign that I want to get, and the rule for getting this sign is the number of interchanges that are required in going from here to here. Let's see if that works out. So here I have done one interchange, and then I have done, so how many have I done? So 1, then APAR, then 2, and then 3. Yeah, so I need 3 interchanges to go from this string to the normal ordered string, which gives me a negative sign in this. So the bracket basically means that you just write the string in normal order, and the rule for the negative sign tells you what sign it will be. I think that is the logic. So this notation of using a bracket on the operator does not include evaluating the contractions. The contractions are separately written as like I wrote in the definition of the contraction. Scroll. Yeah. So here, so this is just the normal ordered string. And since you don't know what sign it will come with, you have this additional rule that tells you the sign by counting the number of interchanges.
So
Yeah, I think I am satisfied now. Yeah.
so you are telling that the answer to the problem would be the delta PQ only, right?
The answer is definitely delta PQ, but this notation is a bit tricky.
So if you do the, I mean, you wrote the contraction of something like AB equals to the total operator minus the normal ordered form.
Yeah.
So if you suppose you write like the APAQ dagger is equal to the, I mean, APAQ dagger contracted equals to APAQ dagger minus the normal ordered form of APAQ dagger, that is AQ dagger AP. Is it possible? Then the rest will follow. Oh, sorry, there will be a minus sign discrepancy. Sorry.
Yeah, so this minus sign discrepancy is sorted by this rule. So I was just wondering why this additional rule is like it looks a bit arbitrary, right? But so then I figured out that this is what makes sense. So when I do an actual real algebra of writing a string of operators in by using the anti-commutation relations, I get some terms, each of which involves at least one contraction, like I said, and I am left with a normal ordered string. Like that is my goal, that I'm left with a normal ordered string. But this normal ordered string is not necessarily of the same sign as the original operator. So what will tell me this sign directly? So this sign is determined by how many interchanges it took me to get from the original string to this normal ordered string. So the sign is not, it doesn't matter what the contractions are. Okay. So it's just the number of interchanges. So that has been rule when you're using this sort of notation of normal ordering as an operator. So does that make sense to you? I think I am more or less satisfied. So if I write any arbitrary string inside A and I say that this is a normal ordered string form of A, then of course I can write any normal ordered form of A when I remove the bracket. So if I carry out the normal ordering operation, I can write any result. But depending on what result I write, I will get a sign, which may be plus, which may be minus. So to find out what sign it is, you have the additional rule that tells you count the number of interchanges that you are doing to get to the normal ordered string. Because this normal ordered string is also not unique, right? It just has the requirement that the creations come before the annihilations. I could have had an AS dagger over here. I could have had AS dagger, AQ dagger, AP, AR as well. And then I would have got a plus sign. Okay. So what tells me the sign of my normal ordered string is this additional rule.
Yes, ma'am.
Yeah. It makes sense now, right? I think it does. Okay. Sorry, sometimes you forget what you've done a long time. Okay, so we can stop here today, I think. Then on Thursday, we will finish Wicks theorem and also the working equations for coupled cluster. And then Friday, if you have any doubts, we'll have a doubt clearing session. And if you don't have any doubts, then I'll try to give an introduction of DFT. Okay. So let's stop here. And I'll let you know about the Viva. I haven't got a clear instruction yet about the Viva. Okay, so let's stop today.